Today, we are going to talk about what might be one of the most beautiful and honestly, one of the most powerful equations in all of science. This is the story of how one person, with an incredible faith in mathematical elegance, managed to unite two of the biggest ideas in physics. And in the process, he accidentally stumbled upon a truth about our universe that nobody saw coming. All right, let's get into it.
So, picture this. It's the late 1920s, and physics is kind of having a bit of an identity crisis. On one side, you've got quantum mechanics, which is just knocking it out of the park describing the weird world of atoms and particles. And on the other side, you've got Einstein's special relativity, which completely changed the game for how we think about space, time, and anything moving really, really fast. The big problem? These two theories might as well have been from different planets. They just didn't work together.
And here's where you can really see the clash. Schrödinger's quantum mechanics, the star of the show at the time, was built for slow-moving stuff. It treats time as this special, absolute thing that just ticks along. But Einstein's special relativity says no, no, no. Time and space are part of the same thing, space-time, and they have to be treated equally. You can see it right there in the energy formulas. They're totally different. You couldn't just take a fast-moving electron and plug it into the Schrödinger equation. The math would just fall apart. Physics had these two incredible theories, but there was no bridge between them.
And then Paul Dirac comes along. Now, Dirac wasn't interested in just slapping some tape on the problem. He thought the issue was fundamental. He set out to build a brand new equation from the ground up, one that had relativity baked into its DNA from the very beginning. And his guiding light through all of this was a deep, almost religious belief in mathematical beauty.
So here's the core of his genius idea. He looked at Einstein's famous energy equation, the one with all the squares in it, E squared equals P squared C squared plus, you know the one. And he asked this crazy question. What if I could find the square root of that equation? What if I could write a new equation that was simple and linear, first order, not second order, just like Schrödinger's was? It was an incredibly bold, almost absurdly elegant goal. So how in the world did he pull it off? Well, he started by just writing down the kind of simple linear equation he wanted. But here was the catch. For this to work, when he squared his new equation, it had to magically transform back into Einstein's original relativistic one. Every single term had to match up perfectly, and when he did the math, he hit a wall. His new coefficients, these alpha and beta things, they couldn't be regular numbers. To make the math work out, they had to have these really weird properties. And no number behaves like that. But then came the breakthrough. Dirac realized that while numbers couldn't do it, matrices could, specifically 4x4 matrices.
And just like that, the Dirac equation was born. It was elegant, it was relativistic, it was perfect. But the math had forced a very strange consequence. Because those alpha and beta coefficients were 4x4 matrices, the thing they acted on, the electron's wave function, couldn't be a single number anymore. It had to be a list of 4 numbers. This was a total head-scratcher. An electron was thought to have 2 states, spin up and spin down. So what were the other 2 components for?
And this, right here, is where the story goes from brilliant to downright magical. See, Dirac wasn't trying to explain all the little mysteries about the electron. He was trying to get quantum mechanics and relativity to play nice. But his beautiful new equation, born out of pure logic, just started handing him these profound physical truths, basically for free. The very first gift from the equation was electron spin. Now, before Dirac, physicists knew electrons had this property, called spin. But it was just sort of tacked on. It was a fudge factor they had to add to the theory by hand to make their predictions match experiments. Nobody knew where it came from.
But get this. When Dirac took his equation and looked at what it predicted for slow-moving electrons, something incredible happened. The 4-component equation naturally split into 2. 2 of the components basically vanished, and the other 2 turned into an equation that perfectly described the electron. But this time, it automatically included spin. It just fell right out of the math. Spin wasn't an optional extra anymore. It was a fundamental property of any particle that obeyed both quantum mechanics and relativity.
Okay, so that was amazing. But the next prediction was even more jaw-droppingly precise. Because an electron has both charge and spin, it acts like a teensy tiny bar magnet. And the strength of that magnet is described by something called the G factor.
And right there in the equation, plain as day, was a term that predicted the G factor for an electron. The number wasn't approximately 2 or kind of close to 2. The equation predicted that G must be exactly 2. I mean, you have to understand why this was such a massive win. Simple classical physics predicted the G factor should be 1, but for years, experiments had shown that for the electron, it was almost exactly 2. It was a complete mystery. And then, out of nowhere,
Dirac's equation, derived from pure theory, just hands them the answer on a silver platter. It was a stunning confirmation.
But the equation had one more secret up its sleeve, and this one was so weird, so deeply troubling, that it almost made Dirac give up on his own creation. Remember how his equation was basically a square root? Well, what happens when you take a square root? You get two answers, a positive one and a negative one. His equation predicted negative energy.
And this wasn't just a mathematical quirk, it seemed to spell doom for the entire universe. The equation said that for every positive energy an electron could have, there was a matching negative energy state. In fact, there was an infinite ladder of these negative states, dropping down forever. So why wouldn't every electron in the universe just instantly fall down this ladder, releasing an infinite amount of energy on the way? The very existence of a stable world seemed to scream that this was wrong. So, to solve this seemingly fatal flaw, Dirac came up with what has to be one of the wildest, most creative ideas in the history of science. He said, you know what? Those negative energy states are real. They're all there. The reason we don't see electrons falling into them is because they're already full. He proposed that what we think of as empty space, the vacuum, is actually a completely full, infinite sea of negative energy electrons.
Now here's where he turned a bug into a feature in the most incredible way. He said, okay, imagine this sea of negative energy electrons. What happens if you hit it with enough energy to kick one of those electrons out, up into our world of positive energy? Well, first, you'd see a normal electron appear out of thin air, but you'd also leave behind a hole in the sea. And this hole, this absence of a negative charge, would look and act just like a particle with the electron's mass, but a positive charge. With that one idea, Dirac had just predicted the existence of antimatter. He predicted a particle he called the positron.
And this wasn't just some sci-fi fantasy. In 1928, Dirac makes this prediction purely to save his theory. Just 4 years later, in 1932, a physicist named Carl Anderson is looking at photos of cosmic rays and sees a track from a particle that looks exactly like an electron, but it curves the wrong way in a magnetic field. It had a positive charge. He had found the positron. Antimatter was real. Dirac had been right.
It's hard to really capture how huge the legacy of this one equation is. It started as a quest to solve a single problem, to build a bridge between two theories, but it ended up redrawing the map of reality itself.
I mean, just look at the before and after. Before Dirac, you had this major conflict in physics. After, it was unified. Before, electron spin was just this thing we added by hand. After, it was a direct consequence of the theory. The magnetic moment went from an experimental curiosity to a precise theoretical prediction. And antimatter? Before Dirac, the very idea was inconceivable. After Dirac, it was a prediction that was quickly proven true. And its influence didn't stop there. By introducing this idea that particles could be created out of the vacuum, out of pure energy, the Dirac equation laid the groundwork for our entire modern understanding of physics, something called quantum field theory. That's the framework we use today to describe all the fundamental particles and forces in the universe. The story of the Dirac equation really is this powerful reminder that sometimes the universe's deepest secrets aren't found in a lab, but in the search for mathematical beauty and consistency. It just makes you wonder, doesn't it? What other incredible truths about our reality are just sitting there, hidden inside an elegant equation, waiting for someone to find them?